Hello everyone, welcome to last week of your classes and last recitation session for fluid mechanics. This week we will have 6 questions and let's start with the first one. This is question 10.24. Here we have a pipe system and we have a given discharge. We need to find the ratio of the head loss in a given length of 1 meter pipe to the head loss in the same length of 2 meter pipe. So we need to choose from these options. So basically what we need is head loss in 1 meter diameter pipe and its ratio to head loss in 2 meter pipe. So basically we have 1 meter pipe here and 2 meter pipe here. And as stated in the question, their length is same. So first let me write the head loss equation from Darcy-Weisbach. We have friction factor, length with square over 2GD. And here we actually have some same numbers. For example, F1 is equal to F2, L1 is equal to L2, and of course G is same, constant. So we can actually ignore these values and we can only focus the ratio between these pipes. So basically the ratio will be V1 square D1 divided by V2 square D2. So this actually gives V1 divided by V2 square times D2 over D1. So this is the simple ratio of these two head losses, but we can actually get more. We can get a number from this ratio. So let me do another calculation here. So here we need to write V1 in terms of D or D in terms of V. So we need to do something for that. So the first equation we can use is continuity equation. This is because the flow rate will be constant for this pipe system, which means V1 A1 is equal to V2 A2. And again, we have V1 multiplied by pi D1 square over 4 and V2 pi D2 square over 4. So again, we have some same numbers here. So from here, we can actually get V1 divided by V2 is equal to D2 square over D1 square. So as you can see, we established a connection between V1 and V2 here. However, in this equation, we actually need V1 divided by V2 square. So that what we can do is just taking square of this equation. So V1 over V2 square is actually equal to D2 D1 the power of 4. And let me continue from here. So this means we can write D2 over D1 power of 4 instead of V1 V2 square here. And we can just keep this value as it is. d2 over d1. And this means we have d2 over d1 to power of 5. So now let's look at their diameters. We have 1 meter and we have 2 meter here. And actually, when we say d2, it is actually 2 meters, and d1 is 1 meter. This means we have 2 to the power of 5, which gives us 32 as the ratio of head losses in these two pipes. So basically, we first created this ratio. Then we said we need to find something between V1, V and D. So we use continuity equation. And then we found out that V1 over V2 is actually equal to D2 over D1 square, and which gives us this relationship. Then once we substitute it in the first equation, we can get the ratio as 32. So the answer is 32 here. This is question 2, 10.40. We have a uncoated cast iron pipe with 4.2 inch, and there's flow, which is 0.08 cubic feet per second, and the temperature is 60 Fahrenheit. And we need to determine friction factor from figure 10.14. So this is actually a body chart that helps us to find friction factor. So for example, if you look at here, we have Reynolds number on the bottom and we have relative roughness on the right hand side. So once we match these two numbers, we will get the corresponding friction factor. So that we need to find Reynolds number and relative roughness. So if you look at here, actually if you look at table 10.4, you are going to find out the roughness for cast iron is 0.01 inch. And if you look at table 8.5, and you will find kinematic viscosity for 60 Fahrenheit. So first, let me find Reynolds numbers. It is velocity diameter divided by kinematic viscosity. Since we have flow rate, we can calculate velocity by dividing this flow rate by the area. So it will be equal to 0.08, and area is pi d square. Since it is inch, we are going to divide it by 12 to make it feet. And then we have 4. So from here, the velocity will be 0.83 feet per second. And then we can calculate Reynolds number, 0.83 feet per second, times the diameter, again divided by 12, and the kinematic viscosity, okay. So this gives 23,811 as the Reynolds number, but we can actually make it 2.33 10 to the power of 4. So this is the first thing we need to know. And the second one is the relative roughness, which we can get by dividing the roughness by diameter. So since both of them are in inch, we can actually directly divide them. So we have roughness of the cast iron pipe, and we have diameter, which is 4.2. And this gives us 0.00238. And now we need to match these two values. So first start with Reynolds numbers. We have 2.33 10 to the power of 4. So if you look up closely, we will see that it will be something around here. So first, let me draw a straight line. And on the right-hand side, we need to find the relative roughness, which is 0.00238. So as I mentioned, as I marked here, it will be something around here. And we are going to draw a curve like other curves, for example, like this one. So we basically draw this line, and we have this straight line, so that we need to find that value. And if you match it with the friction factor on the left hand side, we can see that the value is 0.03. So F is 0.03. Let's continue with question 10.47. Here we have a water with 50 Fahrenheit, and it flows with a speed of 5 feet per second through a horizontal run of PVC pipe. The length of the pipe is 100 feet, and the pipe is schedule 40, which is a pipe type, with a nominal diameter of 2.5 inches. So we need to calculate the pressure drop in PSI, the head loss in feet, and the power in horsepower needed to overcome these head loss. So first, let me write some constant values. So from table 8.5, specific weight is 62.4 pound force divided by cubic feet, and the kinematic viscosity is 14.1 10 to the power of -6 square feet per second. Okay, so here we have velocity and some other pipe types. Diameter of the pipe type. So to find the pressure drop for A, we actually need to use energy equation. And for energy equation, we actually need head loss. And it's also asked in the question. The next one is the power in horsepower. So for that, we are going to use specific weight, floor weight, and head loss equation, which is for power. So for head loss, we can use Darcy-Weisbach equation. And as you remember, it is FL V square over 2GT. So here, let's see what we have and what we don't have. And we have length, which is 100 feet. We have velocity, we have diameter, and we are missing this friction factor. So to find that, if you remember from previous questions, we were using Moody chart. And for the Moody chart, we need Reynolds number and roughness of the selected pipe. Okay. And let me write length, which is 100 feet. So first, start with Moody chart to find the friction factor. It was velocity diameter divided by kinematic viscosity, and velocity is given as 5 feet per second. Diameter is 2.5 inch, but it is equal to 0.20104 feet. And the kinematic viscosity is this value, square feet per second. And this gives 72,400. And it means we have a turbulent flow. So at this step, we can either use Moody chart or we can use some equations that directly gives friction factors. One example for that is Colebrook-White. And in your textbook equation 10.39, there is another equation which is derived from Colebrook-White. It is called Swami, I think, and Jane equation. And this equation is giving friction factor we have log 10, roughness 3.70, Reynolds number, and power of 0.9, and then square. Okay, so the question is directly assuming roughness is 0. So this leaves us with F is equal to 0.25, 10, and Reynolds is 72,400, and this is giving 0.091. So this is the friction factor, and as I mentioned, you can also use Moody chart, and you can compare if there is any difference between these two numbers. Okay, since we calculated the friction factor, we can actually find head loss using Darcy-Weisbach equation, which I gave earlier. So we have 0.0191. We have 100 feet. We have 5 feet per second square. And we had 2 GD. And it will be 2, sorry. Wait second square times the diameter. So this gives 3,635 feet. And this is actually answer for part B in this question, which we were asked for the head loss. And let me open an empty page here. Okay. So now we calculated the head loss and we need the pressure drop and the power in horsepower. And for the pressure drop, we can use energy equation, because if you remember, we have P1, which is the pressure for the first section, and pressure for the second section, so that we can directly calculate this pressure drop. Okay, so we can think this system as a pipe, and the length is 100 feet. And let's say this is section 1 and this is section 2. So we are writing this energy equation between 1 and 2 here. So since we are considering inside of the pipe, and this is a full pipe, so it means we will have pressure, because this pipe is not open to atmosphere, so we cannot ignore pressures here. However, we can still ignore some values, and actually because they are 0. So Z1 is actually equal to Z2, because this is an horizontal pipe. We don't have pump, we don't have turbine, so that we have these values remaining. And velocity will be also same, because there is no change within the pump, within the pipe. So we don't see any change in velocity. So we have P1, P2, and it is equal to head loss. So this actually means pressure drop divided by the specific weight is equal to head loss, which we found as 3,635. So the pressure drop is equal to feet times the specific weight, 62.4 pound force divided by cubic feet. And this is giving 227 pound force over feet square. And if we convert it to PSI, we will get 158 PSI. So this is the answer for part A. And this is what we have more. So lastly, we need to find the power in horsepower needed to overcome this head loss. So power is actually specific weight, flow rate, and head loss. Here, this is the head or the head loss. So we need to write this so that we can find the power required to overcome this head loss. So the specific weight is 62.4 pound-force divided by cubic feet. For the flow rate, we actually didn't explicitly calculate the flow rate, but we can use the velocity given here. So we have 5 feet per second, and area is pi 0.204. And square of this diameter, of course. And lastly, the head loss, which is 3.635 feet. Actually, let me move this equation a little bit below. Okay, better. And from here, we will get, let me see. And actually, the question directly asked for the horsepower. So 1 horsepower is equal to 50 pound-force times feet per second. Okay, so basically, we intended to convert from watt to horsepower, because from here we will actually get watt, because we have pound-force, cubic feet, feet per second, square feet times feet. So we can ignore them. And we have pound-force times feet per second, and this is actually watt. And to convert watt to horsepower, we are required to use this equation. And I directly use that conversion in this equation. And from here, we will get 0.06746 horsepower. So this was the last part of this question. And we calculated all required things like pressure drop, head loss, and power in horsepower needed to overcome this head loss. Now let's look at question 4, 10.51. Here we have a system where water is pumped through a vertical 10 cm new steel pipe to an elevated tank on the roof of a building. The pressure on the discharge side of the pump is 1.6 megapascal, and what pressure can be expected at a point in the pipe 100 meter above the pump when the flow is 0.02 cubic meter per second and the temperature is 20 Celsius. So I draw a figure like this. It is a very basic explanation of the question. But the question says discharge side of the pump. So we can use a we can actually use this point and 100 meter above this distance, let's say here. So it says the discharge side of the pump. This is important because if we want to use energy equation, as you can see, we have HP, which is used for the pump. However, it is actually confusing because we are considering after pump. So, I mean, we have pump here and we are considering the discharge side of the pump so that we actually don't directly consider pump in this equation, so that we don't need to use HP here and we don't need to use, of course, turbine. So it is just the discharge side of the pump here, and the distance from this point, let's say 100 meters here. So we are just considering Bernoulli equation between these 2 points. Okay, so since the velocity will be same within the pipe, because there is no change, there's nothing to change this velocity, so we can ignore v1 and v2 here, and we can take this point as reference, so it will be 0, and in that case z2 will be 110 meters. So the final version of the equation is P1 over gamma, P2 over gamma, 110 meters plus head loss. So the P1 is also given as 1.6 megapascal. We need to find P2, and to do that, the only unknown here is head loss. So as you are familiar, to find the head loss, we are going to use this equation. And again, we know L, we know G, we know D, and we know velocity because we know the flow rate here. And we need to find friction factor here. And again, we can either use body chart or this equation, but we can use this if it is turbulent. So that we need to first calculate the Reynolds number to see if our flow is turbulent or nonlinear flow. So Reynolds VD over kinetic viscosity, and velocity is Q divided by area. Let me move it here. Pi, and diameter is 10 centimeter or 0.1 meter square over 4. And the velocity is 2.546 meter per second. So here we have velocity, diameter divided by kinetic viscosity, and it is given as 10 to the power of minus 6. It is not directly given in the question, but since we know the degree temperature, we can find kinetic viscosity from table. And this Reynolds number gives us 2.55 times 10 to the power of 5. So of course it means it is a turbulent flow. So we can use this equation to calculate the friction factor, or you can also use Moody chart. But let's continue with this equation. So F is equal to 0.25 and we have roughness divided by 3.7 D plus we have 5.74 and divided by Reynolds to the power of 0.9. And of course square of this value. And for the roughness, we can use, let me see if it is given. Yes. It is given as 4.6 down to the power of -2. And this is specific for this kind of pipe. And you can also see find that value from your textbook in chapter 10. So let me write it here. And from here, F will be 2.0183. And now we can calculate head loss. Using das Weisbach equation. The length is 110 meters. The velocity is 2.5. And we have 2 gravitational acceleration times the diameter. And from here, the head loss will be 6.65 meters. And now we can use this equation because the only unknown was the head loss here. So let me write that one here. So for the P1, we have 1.6 megapascal, and I will convert it to Pascal. And we have specific weight. This is equal to P2 over specific weight. It is same. Plus 110 meter plus 6.65 meter. And this equation will give us P2 as 458 kilopascal. Okay, let's solve question 5, 10.69. Here we are using a pump to fill a tank from reservoir as shown. So here we have reservoir and we have tank. So to fill this tank, we are using this pump. And the head provided by the pump is given with this equation. So this means this pump is providing this height, this much of height, so that we can fill the tank. And H0 is given as 50 meters, and Q is discharge to the pump, and the Qmax is given as 2 cubic meter per second. We will assume friction factor as 0.018, and the pipe diameter is 90 centimeters. And this is important. Initially, the water level in the tank is the same as the level in the reservoir. So this actually means when T is 0, it means at the initial step, initial level, the level in the reservoir is equal to level in the tank. So actually at the beginning, it is something like this, so that they don't have any level difference. This means H is 0. The cross-section area of the tank is 100 square meters. So the question asks, how long will it take to fill the tank to height of 40 meters? So again, we have two reservoirs, we have water surfaces open to atmosphere, so we can actually use energy equation. And because we also have pump, so we need to work on the head provided by the pump. So let me write energy equation again. We have H pump here on the left hand side. Velocity head, Z2, and head loss. And we don't have turbine, so we can ignore that. So let's say this is 1 and this is 2. Okay, so let's see what we can neglect in this equation. And as always, we have surfaces open to atmosphere, and we will not have pressure, we will not have velocity. And if we take Z1 as reference, it will be 0, and Z2 will be H, plus we have head loss, and we have pump head. So if we simplify this equation, we will get HP is equal to H plus total head loss. So when we say head loss, again, we will have minor losses and major or friction loss. For the minor loss, let's count what we have. The first one will be here, let's say 1, and this is the loss due to pipe entrance. And we have another one, and this is due to expansion. And the coefficient for the expansion is 1, and for the pipe entrance it is 0.5. So this means we will have 0.5 plus 1 V square over 2G. And for the friction loss, which is the loss throughout the pipe, so we are going to use this Darcy-Weisbach head loss equation. So we will get V square over 2G, and we have F as 0.018. the length is given as 30 meters and the diameter was given as 90 centimeters. So let me write down as well. So we have 30 meters and 0.9 meters. This gives us HP is equal to H, which is the height difference between these two surfaces, plus 2.1 V square over 2G. So this 2.1 is actually coming from this part. And you can also calculate it by yourself. Then in the next step, we can write the HP equation. So in the question, the equation for the head pump is given with this equation. So let me directly write it. HP is equal to H0 1 minus Q square divided by Q max square. And of course, it is going to be equal to H plus we can write 1.05 V square over 2G. So I just directly divided 2.1 by the 2 here. So we have that final equation. And after this step, let me write what we know. So H0 is 50 meters and Qmax is given as 2 cubic meter per second. So we have 51 minus Q square divided by 4 and it's equal to H plus 105 V square over G. Here, let me use continuity equation and let me write velocity in terms of flow rate. Because if we do that, at some point we can write them in the flow rate and we can cancel each other so that we will get the value of flow rate. So from the continuity equation, Q is equal to VA. So instead of velocity, we can write Q divided by area. So we will get 50 minus 12.5 Q square is equal to H plus 105 Q square over GA square. So here we have area and this P d square over 4. And this is the area of pipe, not the area of tank here. And the area is 0.63 square meters. So 50 minus 12.5 Q square is equal to H plus 0.270 And this gives 12.77 q square. So we just move this q square term to right side. And from here, we can get 15 minus h square root is equal to 3.57 q. Yeah. Let me open a new page. So here we have this final equation from the energy equation, but we still have unknowns. And here the question actually gives a very important key point. It says how long will it take to fill the tank? So this actually means dt and dh. So how long will it take to fill this tank, which is 40 meters, in how many times, how many minutes? So that it actually says dh over dt. In other words, this actually means this is meter per second, and this also means this is velocity. So this is important because we can write that flow rate in terms of dh over t, because it also represents velocity, because it is also a meter per second. So as I mentioned, this term says that within this duration, we are filling this tank with the height of h. And for this question, it is 40 meters. So let me write q in terms of velocity times area. And this time we will use dh over dt instead of velocity. And tank, area of the tank. So let me continue writing the equation. We have 3.57 q, or a tank dh over dt. And since we are required to find the duration, which is t, we can leave dt alone. And we can integrate this equation. So if we integrate this equation, we will actually get minus 2, which comes from this part, times 3.57 a tank and the coefficient, constant value. So here we need to find C, because we know area, and we need to find tank, and the H will be 40. But to get C, we can actually use this condition. When T is 0, H is also 0, as I mentioned at the beginning of the question. So this means 0 is equal to and A tank is given as 100 square meters, so we will have 7 minus 714 plus C, and C here will be equal to, actually, so this is also 0 because we said H is 0, so this was H and we are taking it as 0. So C is equal to 714 multiplied by square root of 50. And if we rewrite this equation, we'll get minus 714 and we'll get plus C. So C was 714 and square root of 50, which is 7.071. And here's T again will be 714. So we have 7.071 minus 50 minus H square root. And we need to find the duration for the tank to fill up to the 40 meters. So H will be 40 meters here. And this is going to give us T as 2,791 seconds, or it is equal to 46.5 minutes. Okay, this is the final question, 10.79. We need to find the loss coefficient of the partially closed valve that is required to reduce the discharge to 50% of the flow with the valve wide open as shown. So here in this question, we actually need to find the loss coefficient for this valve, but when it is partially closed. So currently we actually don't know the loss coefficient for partially closed valve, but we know loss coefficient for a wide open valve, and it is given as 0.2, and you can get it from table 10.5. So the main idea for the solution is we will start with assumption that the valve is wide open first. Then we will get some values that is required. And eventually we are going to convert this wide open valve to partially closed valve. So let's start with this wide open valve. Here we have other minor losses as well. And table 10.5 is used for loss coefficient for these minor losses. The first one is pipe entrance, let's say PE, and the loss coefficient for pipe entrance is 0.5. We have two elbows here, and these are 90-degree elbows, so we have 0.9 and 0.9. As I mentioned, for the valve we have 0.2, and lastly there is an expansion here, and for the expansion we will be using 1. So we can actually write an energy equation here, because we can see the relationship between these 2 points, between these 2 reservoirs. So we can take this point and this point as the second section, and this is the first section. So these are just water surfaces of each tank. So we have P1, V1, and we have this energy equation now. So there's a pressure at point 1 and also at point 2. So these are all 0. The velocity at the surface is 0 for both tanks. And if you take Z2 as the reference, it is 0 and Z1 is 2 meters. And of course, we have head loss. And regarding the head loss, we have minor losses and major losses. Major loss means friction loss, which is for the entire pipe. And for minor, we have valve, entrance, and expansion. So if we write head loss like this, so for minor losses, head loss is K V square over 2G. And for major or friction loss, we have FL V2 square over 2GT. So we can write all of these coefficients in the parentheses of V square over 2G. So we have 0.5 from the entrance. We have 0.9 for the elbow. We have wide open valve, which is 0.2. We have another elbow, which is 0.9. And we have expansion 1. Sorry, the previous one was 0.9, and now we have 1 plus the friction loss. So we already have V2 over 2G. So we will just write FL over T. And from here, V2 is equal to 4G divided by 2.5 plus FL over T. So we started the question with the energy equation and we end up with velocity. Because we will calculate velocity based on the wide open valve assumption. And once we found velocity and friction factors, then we can calculate the loss coefficient for partially closed valve. So here, as you can see, we don't know F, but we of course know other values. And to find the F, as remember, we can either use Moody equation, Moody chart, or some other equations. However, for even if you use equation or Moody chart, you are going to need velocity. And because, as you can see here, we have Reynolds numbers inside of this friction factor equation. So for the Reynolds unit velocity, so we can actually directly calculate this equation, because as I mentioned, Reynolds need velocity, velocity need friction factor, and friction factor needs the use of Reynolds numbers. So let me explain this. So for Reynolds, find velocity, and for the velocity, find F, and for F, find Reynolds numbers. So in that case, we usually start with an assumption of friction factor. So we try these numbers, and we try if we can get the same Reynolds number. So for example, let me draw a table like this. Let's say this is trial. First trial, we have F, we have Reynolds numbers. So for example, we can start with an assumption of F is 0.015. And if F is 0.015, the velocity will be 2.65 meter per second. And if the velocity is 2.65, the Reynolds number is 2 times 10 to the power of minus 5. And let me write another F, and let's call this F new. So using Moody chart, if you remember, for the Moody chart, we need to use Reynolds numbers and relative roughness. And here the relative roughness is coming from roughness divided by the diameter. And relative roughness is actually 0.046 millimeters from table 10.4. And D is given as 10 centimeters. So relative roughness is equal to 0.0005. Let me open a new page. Okay, so right now we have relative roughness, we have Reynolds numbers, so this means we can actually find a friction factor value. And based on these two numbers, the friction factor is coming as 0.019. So basically we tried F as 0.015, but eventually we ended up with 0.019. So it means we may require more iterations. And so this time, use this value as the friction factor assumption. And if we have 0.019, then we are going to change the friction factor here. And this is giving us 2.52 meter per second. And once we have 2.52 meter per second, we can get Reynolds numbers. Almost 2 times 10 to the power of minus 5. And since these two are equal or very close to each other, we can find a new friction factor. Actually, the actual number we are getting is 1.9 10 to the power of minus 5. So as I mentioned, since these are very close to each other, we can actually say, okay, these Reynolds numbers are say almost same. So this means we are in the correct path. So we can find the new friction factor. So again, we have this friction factor, these Reynolds numbers, and this relative roughness. So since, as I mentioned, they are very close to each other, we will actually get same friction factor from these Reynolds numbers. So as we see, since we captured the same friction factor, we can stop here. And this means F will be 0.019. So when F is 0.019, the velocity was 2.52, as we can see here. And to make the calculations speed fast, I directly use the final answers here. So you can make your calculations by yourselves. For example, here we have V square, but I directly calculated these values, and also for it's the same for the Reynolds numbers. You will just use acceleration, L and D. And L is given as 14 meters because we have 4, we have 3, and we have 7, which is 14 meters. So here we are just going to use 14 meters as the velocity. And the diameter is 0.1 meters, and acceleration is 9.81 meter per square second. Okay. So the question says, find the loss coefficient of partially closed valve that is required to reduce the discharge to 50% of the flow. So this means we are going to use this partially closed valve, or in other words, we are going to close this valve a little bit so that we will get 50% of the flow. So this means, since we already calculated the velocity once when the valve is wide open, we are going to just close this valve a little bit. Then we will get the 50% of the current velocity or current flow. So this means 50% of flow or velocity, because the area will not change. The decrease in flow rate will decrease the velocity same. So the new velocity will be 1.26 meter per second, which is coming from 2.52 divided by 2. And once the velocity is 1.26, we can calculate the new Reynolds numbers. And it will be 9.5 10 to the power of 4. We are doing that because once we change velocity, it will impact Reynolds number, and the change in the Reynolds number will change the friction factor, and the friction factor change will impact head loss. So from Moody chart, F will be equal to 0.021. Okay. So we are at the last step of the question. So at this step, we will actually use this equation. However, with a difference. So let me try to explain that. So here, we actually use this equation. And right now, we know the friction factor, we know L, we know D, we know G. And here we need to make some changes because, as I mentioned, the valve was wide open, but we need to close it a little bit so that we cannot use 0.2 as loss coefficient anymore. So we need to decrease, we need to subtract this value from the total loss coefficient. In other words, it means we have 0.5, 0.9, 0.9, and 1. And this is giving us 3.3 as the total loss coefficient plus KV. And this is when the partially closed valve. I hope this part was easy to understand. So let's rewrite this equation. So in that equation, V square is 4 times gravitational acceleration divided by 3.3 plus the loss coefficient when the valve is partially closed plus FL over D. F is 0.21, L is 40 meters divided by 0.1 meters. And the velocity was 1.26. So V square will be 1.588, and this is going to be equal to this equation. So as you see, the only remaining unknown value is the loss coefficient of the partially closed valve. So from here, the loss coefficient of that valve will be 18.5. So this part is actually critical because in the first equation, we used 3.5 as the total loss coefficient, but it was when the valve is wide open. But since we are closing it, we cannot use 0.2, which is the loss coefficient for wide open valve, so that we cannot use anymore. So that we need to use other loss coefficients because there is no change in this loss coefficient. But we need to change this valve's loss coefficient. So instead of 3.5, we wrote 3.3 plus the new loss coefficient.